Chapter 2, Section 1, Rates of Change and Limits. We're going to talk about how to evaluate limits. Look on page 62, exercise 8. The limit of x plus 3 raised to the 1,998th power as x approaches -4. Without talking about the meaning of this limit, we're going to just say to evaluate this limit, we simply replace x with -4. So we drop the limit notation, just writing this with -4 in place of x. -4 plus 3 is -1. -1 times itself this many times is +1. That's the answer. We'll talk about the meaning of this later. Many limits are this easy to calculate, like page 63, number 14. The limit of the square root of x plus 3 as x approaches 2. We get the value of this limit by writing the square root of 2 plus 3. X is approaching 2, so we just replace x with 2. Limit should not be in front of this. The answer to exercise 14 is the square root of 5. Number 12, the limit of the int of x as x approaches a half. That would be the int of a half. This is the greatest integer function. The int of a half means the greatest integer that's less than or equal to a half. Of all the integers, 0, 1, 2, 3, etc., -1, -2, -3, etc., this denotes the greatest of all those integers that's less than this. So the answer to exercise 12 is 0. Now, some limits are not as simple as these. Still easy, like number 22, still on page 63. It's the limit as x approaches 2. Actually, it's t approaches 2 of t squared minus 3t plus 2 over t squared minus 4. If we do what we just did in the last few, just replacing t with 2, we would have 0 in the denominator. 2 squared minus 4 is 0. It is not possible to divide by 0. To do this exercise, we copy limit as t approaches 2. We notice the numerator and denominator can both be factored. The denominator is t plus 2 times t minus 2. The numerator is t minus 2 times t minus 1. Bring down the limit as t approaches 2 of t minus 1 over t plus 2, because t minus 2 divided by t minus 2 is 1 over 1. Anything divided by the same thing is 1 over 1. This limit, the limit of t minus 1 over t plus 2 as t approaches 2, is 2 minus 1 over 2 plus 2. Notice where I'm in the step where I'm replacing t with 2, That's when I do not write limit in front anymore. That's the answer to exercise 22. 24. The limit of 1 over 2 plus x minus 1/2. All of this is over x, and x is approaching 0. Noticing that when x is 0, this denominator is 0. Impossible to divide by 0. In previous math courses, like Algebra 2 trig, we would say multiply this numerator by 2 times 2 plus x, because then these fractions won't be fractions anymore. So this is what I'm going to do. I'm going to say 2 times 2 plus x times this fraction 1 over 2 plus x minus 2 times 2 plus x times this fraction 1/2. And I know that if I multiply the numerator that's above this line by this red, I have to multiply the denominator by the same thing. So we're multiplying the numerator and denominator of the original fraction. This original fraction, multiplying numerator and denominator by 2 times 2 plus x. Going down limit as x approaches 0. 2 times 2 plus x times 1 over 2 plus x is just 2, because of this happening. The minus 2 times 2 plus x times 1 over 2 is 1 times 2 plus x, because of this. There's still the 1 and the 2 plus x in parentheses, and the minus 1 all over this denominator. We're just going to leave it like that for now. 2 times 2 plus x times x. Just leave it like that. That's important. Okay, next step, next line. Copy limit as x approaches 0. 2 minus 2 minus x all over 2 times 2 plus x times x. It's just distributing the negative 1. That's how we got minus 2 minus x. And then we have like terms. Limit as x approaches 0 of negative x over 2 times 2 plus x times x. And the reason we left the denominator like this is so that we would eventually be able to cancel this with this, bringing down the limit as x approaches 0. After the canceling of what's in the yellow, on top we still have negative 1, and the bottom is 2 times 2 plus x. X's that are circled in yellow are gone. And this limit is equal to negative 1 over 2 times 2 plus 0. I just replaced x with 0 because x is approaching 0. No limit notation in front of this. Final answer, negative 1/4. So sometimes we have piecewise functions. We'll do a few examples of those. But first of all, we have to write the following. If the limit of some function as x approaches some number from the left is equal to a meaning whatever, and the limit of the function as x approaches the number, the same number up there from the right, is also a, if these are the same, then we say the limit of f of x as x approaches n, here I'm not indicating from left to right, is whatever number we got there. Those have to be the same number. On the other hand, if this ever happens, if the limit of f of x as x approaches n from the left comes out not equal, not the same as the limit of f of x as x approaches n from the right. If this ever happens, then the limit of f of x as x approaches n, period, x approaches n, does not exist. This is when a limit does not exist. Right here. When the limit as x approaches n from the left is not the same as the limit as x approaches n from the right. We're going to look at page 64, exercise 46. F of x equals, this is a piecewise function. There's three pieces. F of x is sometimes 3 minus x. That's one of the pieces. That's if x is less than 2. Sometimes f of x is equal to 2. That's if x is 2. F of x equals x divided by 2 if x is greater than 2. There's three pieces. F of x is different things depending on what x is. When I write the comma, I said the word if. The directions, which are on the bottom of page 63, we're just going to do part B. It says find the limit of this function as x approaches c from the right, where c is 2 in this exercise. But first I ask myself, if c is on the right side of 2, that's telling me c is on the right side of 2, like 2.1, f of x is which one of these? And it's going to be this one, because this is what f of x equals right here, if x is greater than 2. Greater than 2 means on the right side of 2. So we rewrite this question by replacing the f of x with x over 2. The limit stuff in front just gets copied. Because f of x is gone, one of these is in its place. But it's this one, x over 2. And then the limit of x over 2 as x approaches 2 from the right, we find that by just replacing x with 2. Once we get here, the from the right is irrelevant. Approaching 2 from the right is there to tell you which piece to use. But then we find the limit by just subbing in the 2. It also asks in the directions for the limit of f of x as x approaches c from the left. It says find the limit of f of x as x approaches c, we're talking about the number 2, from the left. If x is on the left side of 2, say 1.9, f of x is this piece. If x is approaching 2 from the left, that means x is on the left side of 2. Numbers on the left side of 2 are less than 2. That's why we rewrite this as the limit of 3 minus x as x approaches 2. And we from the left. Even though I'm writing x approaches 2 from the left, we just plug in 2. It's not approaching 2 from the left to tell me which piece to use. Alright, so that's that. Then part C says, does the limit of f of x as x approaches 2 exist? So we're going to say the limit of f of x as x approaches 2 exists simply because these answers were the same. And we say the limit of f of x as x approaches 2 is that same answer that we got for both of those. So technically this one is the limit as x approaches 2 from the right. This one is the limit as x approaches 2 from the left. And because they're the same, we say the limit as x approaches 2, period, is 1. We'll do, I'll just reiterate that if these had come out different, which they could have because we plugged 2 into 2 different things, if they had come out different, we would have said the limit of f of x as x approaches 2 does not exist. All right, next we're going to do number 58, which says, a rock released from rest to fall on a small airless planet falls y equals g t squared meters in t seconds. So y, whatever y is, it's measured in meters. The t in this formula is measured in seconds. G is some constant. Suppose the rock falls to the bottom of a crevice 20 meters. It's telling me to replace y with 20 because y is some number of meters. And it reaches the bottom in 4 seconds. T is measured in seconds. So we have 20 equals 16 g. Divide both sides by 16. 20/16 can be reduced to 5/4. So what we have here is, without even reading part A, we've done it. Just by reading what's given, we ended up answering part A, find the value of g. Now parts B and C. Part B is asking for average speed. So this is one of the most important things in calculus. The phrase average speed is simply the change in y divided by the change in t. The letters are not really important, it's what they represent. Since y is measured in meters, this numerator is meters. Since t is measured in seconds, this denominator is seconds. So whatever we get when we calculate this division, its units will be meters per, think of division as the word per second. Meters per second is how we have, is one way to measure speed. A lot of other ways, like miles per hour, feet per second. And in this problem, y is measured in meters, so delta y, or change in y, is the numerator, and t is measuring seconds, so delta t is the denominator. So we end up with meters per second for average speed. So this notation is important. In this problem, delta y means the y evaluated at the later time, 4 seconds is how long it took to reach the bottom, minus y evaluated at the starting time, which is 0 seconds. Change in y means we're subtracting the y's. Change in t means we're going to subtract those times. The later time minus the earlier time. And y of 4 means 5/4 times 4 squared. And y of 0 means 5/4 times 0 squared. Because for the y I'm using this, y equals gt squared. Y equals g t squared, using that formula from the given and the g that we found. That's 16 times 5/4, which is 20. That's 0 times 5/4, which is 0. So the 20 minus 0 is meters, 20 meters. So 4 seconds to do that. So that's 5 meters on top. These are seconds on the bottom. 5 meters per second is the average speed over the 4-second time interval. 4-second time interval. This is key. All right, for part C, this is going to be new to you. Part C is asking for the instantaneous speed, the speed at which the rock hits the bottom. We call that instantaneous speed. A speed at an instant. The definition, this is really important. This is what calculus is all about. Speed at an instant is the limit as h approaches 0 of y, where if y is measured in meters, of t plus h, keeping in mind that h is going to approach 0, minus y of t all over h. The h denominator is really a change in time. We need seconds on the bottom to have a meters per second answer. But we're going to make the h, the change in time, become 0. If we're finding the speed over an interval of time that's 0, that means we're finding the time at an instant. So part C is asking for the speed at which the rock hit the bottom at that very instant. In other words, the limit as h approaches 0 of the y, the position function, at 4, that's when it hit the bottom, plus no time minus y of 4 all over h. This is finding the speed at exactly the instant 4, because that is exactly the time that it hit the bottom. That's the instant. The h will be 0. Amazingly enough, because we can't divide by 0. But we can do algebra. In the function, which was y equals 5/4 t squared, in this function y equals 5/4 t squared, this right here means replace the t with 4 plus h. So 5/4 times 4 plus h squared. And I'll repeat that in a couple minutes or second. Y of 4, this right here, means go over here and replace the t with 4. So function notation, y of 4 means replace t with 4. Y of 4 plus h means replace t with 4 plus h. Think about that. So we still have h approaching 0. We still say can't divide by 0. By the way, this red and blue step is the most important. Make sure you understand where that's coming from. Think about it for a while. The rest is easy algebra. Ready? 4 plus h squared means 4 plus h times 4 plus h, which is 16 plus 8h plus h squared. 4 plus h times itself. This blue, 5/4 times 4 squared is 20. 16 times 5/4 is 20. All over h. Copy the limit as h approaches 0. Distribute. 5/4 times 16 is 20. 5/4 times 8h is 10h. Is the 84th. I mean, it would be 44th. Plus 5/4 times h squared. That's 5/4 h squared. Bring down the minus 20 and the over h. So we just distributed 5/4 so there's no parentheses anymore. Copy this, limit as h approaches 0. Notice there's a 20 and a minus 20, so 10h plus 5/4 h squared all over h. 20 minus 20 is 0. Notice both of these terms have h. Common h can be factored out of 10 plus 5/4 h all over h. And now we get to cancel the h's. Limit as h approaches 0 of 10 plus 5/4 h, because we canceled. Lots of people will completely skip this step because they can do this division mentally and go right from here to here. 10h over h is 10. 5/4 h squared over h is 5/4 h. And the limit of this as h approaches 0 is 10 plus 5/4 times 0. H is approaching 0. And 10 plus 5/4 times 0 is 10. The units on this answer 10, and from up here, the numerator was a change in y's. That's measured in meters. The denominator is a change in time, which is seconds. That's why the answer is 10 meters per second. That's the speed at which the rock hit bottom, at the very instant that it hit bottom.